Welcome everyone back to the second day. This is the morning session, and the first talk will have Rosa Valenti from University of Frankfurt, and talking about exploring non-local correlations in iron-based superconductors theoretical approach. So, Rosa's floor is all yours, I guess.
Yes, thank you very much, Ming, and thank you very much to all the organizers for the opportunity to present our results. So today I would like to discuss the possibility of the role of non-local correlations in iron-based superconductors. And as I was telling to Himiao, since I am in a session where topology is an important topic, I would like also to present very recent results on prediction of double Weyl points in these materials. First of all, I would like to thank my collaborators, so especially Karim Santu and Stefan Backes for the work on non-local correlations, as well as Niklas Heinsdorf, Morten Christensen, Mikel Iraola, Turan Birol, Rafael Fernandez, and Christian Batista for the work on Weyl points. So if we consider the generic phase diagrams for the iron-based superconductors in a temperature versus doping or pressure representation, we know that we have a superconducting phase in the vicinity of some magnetic phase or phases, nematic phases, structural phases. And along the years, we have been having new type of phases coming into these complex phase diagrams, which are a consequence of a subtle interplay of charge, spin, orbital, and lattice degrees of freedom. And what I want to concentrate today is on the role of local versus non-local correlations in some of these phases, as well as possible new topological states that can emerge in these materials. And let me start with correlation effects, how important are in these materials. So we start with a description of a non-interacting electronic system. So basically we can describe the system in a K representation, so in the reciprocal space representation, as basically having quasi-particles that have an infinite lifetime. And now when we start to switch on correlations, a strong interaction among these quasi-particles, what we observe is a transfer of a spectral weight in what we call the lower and the upper Hubbard band. And the way of mathematically describe this process is, for instance, when we consider a Green's function representation, is in terms of a self-energy, which has in principle momentum and frequency dependence. So what about now focusing on the iron-based superconductors? Where do we see traces in experiment of these electronic correlations? And of course, there is many different probes to just observe these correlations effects. I will concentrate mostly on angular resolved photoemission experiments where one sees strong band renormalizations, but there are many other experiments like the Haas van Alphen, optical conductivity, thermodynamics. So for instance, Himiao did at the very beginning of the iron-based superconductors together with his colleagues, a very nice investigation of the effects of correlations by just looking at optical conductivity experiments. So just to show you that this discussion of correlations in the iron-based superconductors is just a discussion that already started in 2008. So what I want to do today is concentrate on these renormalization effects that we see in angular resolved photoemission experiments, and to just see how strong bands are renormalized. I will first concentrate on lithium-ion arsenic. This system, we had yesterday a very nice talk about recent ARPES measurements on this material. It's a nice test bed materials to, in fact, investigate these correlation effects, because the system doesn't show a structural phase transition, doesn't show a magnetic phase transition, doesn't show nematicity. Basically, it's a system in the tetragonal phase that goes superconductor at 18 Kelvin. And as you can see, these are ARPES measurements from Borisenko and collaborators, and there are, of course, in the literature, many ARPES measurements, but what I want to show you here is the Fermi surface around the gamma point, where one observes that the inner Hall pocket is strongly renormalized with respect to what we obtain by doing, for instance, LDA calculations. And in fact, this just to see that there is a strong, there is basically the inner Hall pocket shows a flower-like basically shape. So I'm showing here for the experiments just to see this strong renormalization. Now, a theory that has been very successful in describing these effects of correlations in these iron-based superconductors is dynamical mean field theory, which yesterday there was a session on where this was in fact discussed. And the idea of dynamical mean field theory is to replace the system of interacting orbitals into basically a system of one central site, which is dynamically interacting with a bath given by the rest of the sites. And in fact, this combination of dynamical mean field theory with density functional theory has been able to describe many trends observed on the correlations in these materials. So for instance, going back to the Fermi surface description, what we see, these are the LDA calculations, these are LDA plus the MFT. We see this trend of renormalization of these inner Hall pockets getting more shrunk as it is being seen in experiment. But what is a most important result of this type of calculations is the fact that the correlations are orbitally selective. So different orbitals show a different degree of correlation. And there is in fact a recent review by our organizers on these effects of orbital selectivity. And there is also, in fact, this new concept of Hund's metal, which also applies nicely to these materials. So the second feature that I wanted to mention that also the MFT is able to very nicely describe is this transfer of a spectral weight creating Hubbard bands. And here I'm showing results for iron selenium, which is one of the materials thought to be most strongly correlated, where I'm showing the photoemission experiments from Amalia Coldea, Matt Watson and collaborators. And we did here DMFT calculations just to show that one can identify this transfer of a spectral weight as a lower Hubbard band. And even more information can be obtained from these calculations by doing, in fact, this orbital, by looking at this orbital selectivity, what is causing, which orbital is most correlated, showing this effect of the lower Hubbard band. However, even that there is a lot of success in these type of calculations, there are features that in principle this conventional type of doing DMFT, so what we call the one-side DMFT, is not able to reproduce. So DMFT, the one-side DMFT, can describe exactly local correlations, but has no information on non-local correlations. And there is an effect that was already seen a long way back by in some family of these, in some materials of this family of iron-based superconductors, which is what it's called the Blu-Ray Shift. So the Blu-Ray Shift is the following, that the renormalization of the bands at the gamma and at the M point is going in the opposite direction to what a usual DFT calculation would show you. So if this goes in the opposite direction, so there is a shift to the blue and a shift to the red, this cannot be explained in principle in terms of theory that includes correlation effects only at the local level. So therefore, this was type of experiments was calling for a description where non-local correlations, so momentum-dependent correlations are included. And in fact, there are a few reports on scattering rates where it is claimed, these measurements, it is claimed that there is a strong momentum dependence. So what we did here is to consider a different type of approach to calculate the self-energy dependence that includes also a momentum dependence, not only frequency dependence. And this is by considering the two-particle self-consistent method, which was initially introduced for the one-band Hubbard model by Wilk and Tremblay. And this method, the idea of this method is to start, in fact, by analyzing two-particle correlations and doing some approximations to them. In the way that these approximations are done is by fulfilling different type of sum rules. And at the end of the day, by doing this type of approximation, which is valid for weak to intermediate coupling, one can obtain, in fact, these momentum and frequency dependent self-energies. So we applied that to lithium-ion arsenic, and here I'm showing this is the results of the band structures of the Fermi surface by DFT. And when one applies this combination of DFT with this two-particle self-consistent method to obtain the effect of the self-energy, what one obtains is, in fact, a result, a shrinking of these inner hole pockets, very similar to what is being observed experimentally. And moreover, what is very interesting is that if we now average these results, we do the momentum average, what we obtain is the result of the MFT. So in fact, these two methods, even though these are these two type of approaches, different approaches to obtain self-energies, one can obtain the other by doing an average of over the momentum. So let's look now at this red-blue shift or blue-red shift, depending on where you define the blue and the red. How is this described by this type of approach? So what I'm showing here is the band structure. In these green lines is the DFT band structure for lithium-ion arsenic, where I did a rescaling of 2 in order to be able to compare better the bands. And the color mapping is the result of this DFT plus TPSC, where yellow means more intensity. And one can see, in fact, indeed, there is this shifting down of the bands at the gamma point and the shifting up towards the Fermi level at the M point. So this blue-red shift is well described by this type of approximation. And the point is that the reason why there is this blue-red shift is because of spin fluctuations at the vectors 0, pi, and pi 0. So that the contribution at gamma and the contribution at M are of different signs. And that's why there is this red-blue shift. So we have also calculated the energy dependence of the quasi-particle lifetimes because we could compare with experiments. So these are experiments by the group of Véronique Brouet, where what I'm showing here is the energy dependence of the quasi-particle lifetimes as I go from gamma to M. So let me show you the one. So this is the inner hole pocket is the named by 1, and the inner electron pocket named by fear. These are the red pockets, and these red pockets have a rather linear behavior. I mean, this can be observed here also in these calculations because it looks very incoherent. So this is the result of the experiment. And these are the results that we obtained with TPSC. So we also obtained this type of linear dependence in omega. While the pockets, the whole pockets at 2, so basically these outer hole pocket and these outer electron pockets, they have more quadratic behavior, as it is also seen by experiments. So these theories seem to capture these features observed in RPs. So that with this type of calculation, what we can say is that a momentum dependent type of effect in the self-energy is able to explain many features of these RPs observations. I should mention also that very recently, Kim, Antoine George, Gabi Codley, and collaborators, what they did is a different kind of calculation. So they did basically GW plus what they call ansatz DMFT, so that they are including all contributions of the long-range part of the Coulomb repulsion. And by doing this type of approach, they seem also to be able to explain this type of features. So that here, I think this would be an interesting subject for discussion. One scenario, which is the scenario I am presenting, is more describing this type of effects in terms of the low energy spin fluctuations, while the scenario 2 is describing this type of effects in terms of the long range part of the Coulomb repulsion. So this, I leave it as an open discussion. Let me go now in my last 5 minutes to the topology part of my talk. And I'm now changing the iron-based superconductor I would like to focus on. So I'm going to go into the so-called 1144 materials. And what I want to show you is that by considering a combination of spin-orbit coupling, magnetism, and the very special structure of these materials, one can predict the presence of double Weyl points. Let me show you that step by step. So first of all, the materials I'm talking about are, for instance, calcium, potassium, iron 4, arsenic 4. So these materials have the same structure as the 1 to 2 materials, but what we have in this case is that there is an alternation of cations, so calcium, potassium, calcium, potassium, what makes this a structure that the unit cell is 2 iron planes per unit cell. And because of these different cations, we are breaking explicitly the glide symmetry that is otherwise present in all iron-based superconductors. So what we have in this material is there is no glide symmetry. And because there is no glide symmetry, there is also no iron plane inversion symmetry. However, the symmetries I will concentrate on in order to get to these Weyl points is the fact that this system has a C4C symmetry along these vertical axis and still keeps an inversion symmetry which is centered at these cations, calcium or potassium. And the bands that I want to now concentrate on, so contrary to the topological effects that we, for instance, saw yesterday, where there was a crossing between a D and a P band, so a D band of iron and a P band of arsenic, what I will be concentrating today is only on D bands. And on this path along the Brühling zone, the MA path, which is the path along from pi pi 0 to pi pi pi. So let's first do a symmetry analysis along this path. So what I'm doing now is by considering basically these special symmetries of calcium, potassium, iron 4, arsenic 4, I just can evaluate the irreducible representations of the bands along this path of the Brühling zone. And let me concentrate on this MA path. So what we have, if we consider the fact that I have a glide plane symmetry broken, that I have a C4C symmetry, and I have an inversion center at the calcium or potassium, what we will expect is to have nodal lines along MA, which are fourfold degenerate, twofold because of the C4C symmetry and fourfold because of the Kramer's degeneracy. And I have two sets of them because calcium, potassium, iron 4, arsenic 4 has 2 iron layers per unit cell. So now what we want to do is basically this fourfold nodal line, we want to break all the possible degeneracies to get at the end of the day just non-degenerate bands where a possible crossing can happen. So one way of breaking this degeneracy is by applying a magnetic field along Z. So we are going then to break the Kramer's degeneracy, and we will just get here twofold nodal lines. Another way of breaking this degeneracy is by including the effects of spin-orbit coupling in this system that will also break this degeneracy into twofold bands. So if we combine the two effects, spin-orbit coupling and an application of an effect of a magnetic field along Z, at the end of the day, indeed, we are going to have non-degenerate bands. And what the symmetry analysis is telling us that there is the possibility of having a crossing along this MA direction, either a crossing where the bands have the same spin polarization, but opposite angular momentum polarization, and this will give rise to a double Weyl point, so in fact, a pair of double Weyl points, or in the case that the magnetic field is not that strong, we can have a crossing between bands that are of opposite spin polarization, and then we will have a Weyl point of charge plus or minus 1, so a pair of those. So now we go to the real system and do the calculations, and we apply the magnetic field along the Z direction so that the the polarized iron has a magnetic moment of about 0.6 mu Bohr. And by doing this calculation, what we find is indeed that we get a double Weyl point along this line. So at plus kz and minus kz, and in order to show you that it is indeed the double Weyl point, as the symmetry analysis is telling us, analyzing the band structure near this double Weyl point is indeed a band touching, which is quadratic in the kz-kx plane, and it's linear along the it's quadratic along the ky kz and linear ky kx and linear along kz. And the two Weyl points, this is a picture of the very curvature, so the flux of the very curvature, which shows us that one, it is basically the flux is going out of the Weyl point, and in the other one, it's going in. So one is a source and the other one is a sink. And one can also calculate basically these Fermi arcs that are connecting these two Weyl points. So with that, and I think my time is over, I come to the end of my talk. So the second part was to show you that it is possible to have magnetic field induced double Weyl points in these 1144 materials by application of a magnetic field. And in fact, the Weyl points that we found are very near the Fermi surface. So for instance, by using the doped materials, so in order to bring down the Fermi level, one could have these Weyl points at the Fermi surface. And what it may be very interesting is to investigate the interplay of superconductivity and topology. And the first part, what I showed to you is that the effect of non-local correlations in iron-based superconductors in order to understand some features of the spectral function in these materials. And with that, I would like to thank you for your attention.
Thank you, Rosa, very much for this great talk. Any questions from the audience? Well, while the audience is thinking of questions, may I just ask one question to start? Sorry, yeah, and then David, yeah. So Rosa, so is the splitting of the bands in the last part just the Zeeman, the energy scale on the order of the Zeeman splitting? So you want to resolve this?
Yes, so exactly, this one, right?
Mm-hmm.
This. Okay, so the order of the Zeeman splitting, in principle, if I want to get this double Weyl point, is rather large. So it means I have to apply rather strong magnetic fields. So that's why what we did is so basically we extracted the order of magnitude from the polarization of the magnetic moment. So we need to polarize them along the z direction with a magnetic moment of 0.6 mu Bohr. So it's going to be large magnetic fields, but I think it's doable, at least with the sources that one has. So I think it's optimistic. Otherwise, of course, what you will get is single Weyl points, which is also an interesting. So to reach the double Weyl points, the magnetic fields have to be large.
I see. Thank you. I think next, David, do you want to ask your question?
Hi, this might be a bit dumb, but I'm not sure I understood what's the difference between a double Weyl point and a Dirac point. Is there a brief way to clarify that?
Yes. So the double Weyl, okay, so the double Weyl point is in this case, these are Weyl points that come because the bands they have non-degeneracy, while in the Dirac points we have degenerate bands touching. And in this case, we have bands of the same polarization, but it's the angular momentum which is opposite. And this gives rise to these double Weyl points, which means that along in the direction perpendicular to z, so along the kx and ky, I'm going to have a quadratic band touching, while along the kz direction, I'm going to have a linear band touching, like in the single Weyl points. I don't know whether this was clear.
So was the major distinction about the band structure, like the quadratic?
The basic distinction, so maybe let me show it here.
Or the angular momentum?
the angle, so the major distinction is that a double violet point is a quadratic band touching, while a single violet point is a linear band touching.
I see. Okay, thanks.
And then Timiao?
It was a really nice talk. So just sort of going back to this theme of what is universal across these ion-based superconductors and what is not.
Yeah.
I thought it would be to the first part of your talk.
Yes.
So lithium-ion arsenic. So it's interesting to ask, how does it compare with FeTe SE, a material which is of a lot of interest for a variety of reasons. So there, actually, the chair showed that you have this orbital selectivity, but the gross level, you can just raise the temperature and see that some of these orbitals, the spectral weight just go away, and the others don't, right? So dxy is where it goes away, and there's some temperature scale for that. Now, and that was one of the sort of indications where local interactions play an important role. Now, in lithium-ion arsenic case, that the APES experiment was also done, and the temperature scale is a bit higher, 200, slightly more than 200 Kelvin, but also the XY orbital spectral weight goes away at that temperature. So I just wonder whether in this discussion of non-local correlations contributing to the renormalization of the electronic band structure here versus local ones, how does that seemingly zeroth order feature factor into the consideration for you?
Yeah, I mean, this is a very good point, because that's why we're having all this discussion with Antoine and with and Gabi, because you want to find. I agree with you that it's not a simple problem, okay? And in fact, you are talking about iron, selenium, tellurium, iron, selenium, sulfur, all these systems. In fact, the iron selenium is in some sense is more complex than, in my view, than lithium-ion arsenic. It's more complex because we have there more features that we still don't completely understand, like, as you say, disappearance of, depending on the temperature, also disappearance of some spectral weight. That's why we chose this material, which seems to be, I classify it as less strongly correlated. I mean, it's correlated, but less strongly correlated. And maybe we don't have to deal with these extra features. But I completely agree that it is, so what I saw here is that this could be a scenario to understand some of these features, but probably not, it's not, with that, we're not settling the whole problem. And that's why we're discussing also with Gabi, what about the long-range Coulomb interactions that we know that they are also influencing that. And at the end of the day, the question is, which of all these different contributions is the one that maybe dominate, or it's all of them at once? Or this, I think, is something we need to think about a little bit further. But it's not a simple problem. I just wanted to show that by doing such a type of approach, one at least is able to understand some of these properties in terms of spin fluctuations. This is basically what this approach is giving you, that spin fluctuations are important in these materials. But it's not the only ingredient. We need to also include charge fluctuations, and the charge fluctuations in this type of approach are only included at the what I call at the low energy level. So wherever I do the cut. So it's not an integration over all energies. And this is something one has to work out still.
Yeah, fair enough. So continue this discussion.
Thank you. And one more question from Peng Cheng.
Yeah, so I was very curious on your last part. When you turn on the magnetic field, you induce this well points. So what are the sort of experimental signature you might expect from spin fluctuation point of view? Assuming you do such a Duncan experiment, putting a large magnetic field.
Yes. So what I expect, if you put a large magnetic field, and then you are able to basically separate these these bands so that you don't have a mixing of the two polarizations.
Right, right.
And now I'm showing it here. This of course depends on the features of your material, but in this material, what I expect if you put a magnetic field and you are able to bring this on the surface, so by using the dope, you should be able, depending on the experiment you do. So if you do a transport experiment, so you should be able, for instance, to see these effects of these Fermi arcs. If you do an ARPES experiment, the question is with magnetic field, I think there is no possibility, right?
Right.
So there is no way, but transport, yes. So one would see, in fact, a lot of anomalies in transport experiments. For instance,
I'm curious on the spin fluctuation. I mean, what would you expect the spin fluctuation will respond?
Yeah. Okay. So this system, and in fact, this is an ingredient I didn't talk about. This system we know. This system we know that. In fact, when you dope it, when you electron dope it, it shows this order, this spin vortex order. So we know that and there are, in fact, for this material, there are NMR data that show these spin fluctuations that come from a vortex type of fluctuations. So what we expect is that these vortex fluctuations are going also to influence the presence of this type of bile points. Is this the question you are posing?
Yeah, no, yeah. I mean, basically, I mean, this stuff is known to have an income. Believe it's income-induced, some sort of income-induced spin fluctuations, right, or something.
No, vortex. This system is a vortex. So this vortex will definitely enhance this type of topological points. So this type of features.
Okay. Yeah. Thank you.
So they work towards it.
Sorry, when I just ask one last question based on the slide.
Yes?
Sorry.
On
So
this one?
it's like, yeah, the slide. So it seems like so every set of bands from M to A has this property, right? Is that just
well, from M to, at least you can find, exactly, in principle you can find many of these bunches of bands where you could indeed find these features. Yeah, I mean, all these D bands, these are all D bands.
Yes.
So the only problem is that, of course, if you have a lot of hybridization with, let's say, arsenic, then it's going to be more obscure to find these crossings. So, but it's true, from the symmetry point of view, you should be able to find these in all these bundles of D bands that are along this path.
Okay, thank you very much. Thank you for this very nice talk, Rosa.
Thank you very much. So I'm stop sharing.
Yes, and then next we have Vidya Madhavan from UIUC. Vidya, you can start sharing your screen.
Okay, let me actually turn on my video somehow. There.
Great.
Hi, everyone. Good to see you all.
You want to play and see if we can get the correct screen?
Yeah, what do you see?
Perfect, that's the right screen.
Okay.
We have Vidya, right. So Vidya, I guess, yeah, from UIUC, and she was talking about signatures of dispersing material modes in approximatized topological material. So.
Okay, thanks a lot. Thanks, Ming and the organizers for inviting me. It's been a very interesting series of talks and discussions. I was there last night when people were talking about all the different bands crossing the Fermi energy. And I'm going to show you some band structure, but I have to dissemble right now. I'm not going to attribute any of the bands to any of the orbitals, because I'm not actually sure of the orbital assignment after listening to all these talks. Okay, with that, let me just go forward. So actually, I'm going to deviate from many of the talks that have been about correlations. And the previous talk was about wild points, and here I'm mostly going to talk about some topological aspects in this material. So a lot of the STM work I'm going to show you today was carried out by my former postdoc, Zhenyu Wang, who's actually a faculty in China right now, with the help of graduate student George Rodriguez. And I suspect I won't get to this, but if I do get to this, I'd like to show you some monolayer FE-SET films that we've grown on bismuth telluride. And this is really intriguing because these monolayer films behave exactly like the bulk compounds. And there's a lot of interesting physics there, but I have a feeling I might not get to it. In any case, that work was done by my graduate students, Guanan Chen and Anuba Aishwarya. We had a lot of theory help from Taylor Hughes and Dirk Moore. And the single crystals of FE-SET I'm going to show you today in today's talk, we got from Genda Gu's group in Brookhaven. So essentially this talk is about this particular idea, which was proposed by Charlie Kane and Liang Fu in 2008, which is that if you could take a topological insulator and proximatize it with a superconductor, then it's a great platform to realize different kinds of Majorana states. So for example, in such a system, if you could turn on a magnetic field, then you would expect to see inside the vortex cores, in the proximatized topological insulator, you should see zero bias Majorana bound states. Also, if you have, by some clever engineering, if you could put two superconductors with a pi phase shift, or in fact, as it turns out, any phase shift on top of this topological insulator, then at the boundary between these superconductors with different phases, you expect to see propagating Majorana fermions. So the signatures of these vortex-bound states would be seen, for example, in STM spectroscopy as a zero bias peak inside the superconducting gap. And if you were to achieve this geometry where you have this pi or a phase shift between two superconducting regions, then at the boundary, you should see dispersing Majorana states. And these Majorana states should be helical states, and they should have linear dispersion. So in today's talk, I'm going to show you STM data from my group as well as other groups. And I think what I really want to say is that if you just take one data set by itself, it's not very convincing. But if you add all the pieces of information together, then it seems pretty certain now that we are able to realize Majorana modes in these kinds of proximatized systems. So in 2015, there was this idea, this proposal that FE-SET has in fact one band that is inverted at the gamma point. And because of that, it's topologically non-trivial. And due to its topologically non-trivial nature, it has topological surface states. So the beauty of this, of course, is that since this is a superconductor, you have this kind of an intrinsic proximatized superconductor where the topological surface states become superconducting by proximity effect. And now you have in one system this ability to realize Majorana fermions. So this is the phase diagram, and you're all very familiar with it. I'm not sure how big this box is supposed to be, but somewhere around this composition is where this band inversion is expected to happen, around 50-50. And so this is what I was telling you at the beginning of the talk. So here's a very superficial band structure. All I want to point out here is in these compounds, at least in the 50-50 compound, what you expect to see is two whole bands at the gamma point, and two very closely related electron pockets near the M point. So for convenience, we'll just call the whole pockets alpha and beta, and the electron pocket gamma. So basically, you have these band crossings. And as I said before, I don't want to assign any orbital character. Maybe we can have a longer discussion about the orbital character of these things. But what really is expected to happen is that as you go from any of the N members, FESE or FETE, to the middle, this P band and D band, they come closer. And once they meet each other and reopen a gap, that's when you have band inversion. And that happens for some range of compositions in this compound. But because of this band inversion right here at the gamma point, you expect to see topological surface states. And that's what Hongding and Shixin showed in 2018. They did RPES, and what they could see is linearly dispersing states inside in this sort of narrow region right here near the Fermi energy. So now let's actually see some STM data. We have multiple STMs in my group. All of this work that I'm going to show you from my group at least was done in the commercial system, bought from Unisoku in Japan. And it can go to 300 millikelvin and it has 11 Tesla field. Okay, so this is the crystal structure. You're all very familiar. One thing I do want to point out is that the top selenium atoms and the bottom selenium atoms are shifted from one another. And in STM, of course, you only see the top selenium atoms, which I have marked in orange here. And one thing to notice here is that this is the position of the bottom selenium atom. And if you think of this as your just a tentative unit cell, then this thing is shifted by half a unit cell, right? So this crystal structure has this propensity to have domains where, in some region, this might be the top selenium atom, but then there might be other regions nearby where this thing simply flips. So what you'll see is a domain wall with a half unit cell shift, and that's going to be important later on. So these are really beautiful samples that we got from Gendagu. This is a large area topography. And if you zoom in, you can see the selenium, and this is, a mixed compound, FeSET. So you see bright and dark spots, and then so this is almost 50-50 selenium and tellurium. The reason I say that this is a very beautiful single crystal is that, a lot of these FeSET materials are plagued by excess ion. And the problem with having excess ion is it actually suppresses the superconducting gap. And you could anneal the samples to get rid of excess ion. But in this case, as it turns out, these samples that I'm showing you, you can see this in this large field of view. This is maybe just one little excess ion, or maybe this one here, that's it. We didn't have to anneal these samples. And because of the quality of these crystals, what you can see very nicely when you take STM data is a beautiful superconducting gap with a very flat density of states. Now, this here is a line cut. It shows you spectra taken along this line. And what you see immediately is A, there are multiple coherence peaks, right? You can see one here, and so on. And B, these coherence peaks actually shift around as a function of position. So it's obviously electronically inhomogeneous, and there are multiple gaps. And these multiple gaps come from these various pockets that I was talking about earlier that cross the Fermi energy. And if you take data from specific heat, RPES, optical conductivity, etc., and you put it all together, basically you find that in a sense, you should see, you have these two hole pockets are expected to have a gap of approximately 1.5 MeV and 2.5 MeV. And what I talked about earlier, which is the topological surface state, is expected to have a gap of 1.8 MeV. So leaving aside this larger gap, if you look at the, the energy range between 1 and 3 millivolts, what you should see with STM is actually 3 distinct coherence peaks associated with these 3 bands, 2 of which are the bulk bands, and 1 of which, this one, is the surface state. So let's ask if we actually see this. And so we can go and measure the gap at each position. And as usual, we can, this is what I would call a gap map. But the most important thing here is that there are regions here where you see 3 distinct gaps. And if I do a gap histogram, this is a statistical analysis from, thousands and thousands of spectra, then you can see that we do have 3 distinct gaps, although the histograms, this is because of inhomogeneity. With mean values, the gap values have mean values of 1.3, 1.8, and 2.4 MeV. The reason this is important is because then you can compare to ARPES, and you can assign, that this particular low energy gap at 1.3 MeV is the alpha pocket. This is the topological surface state, and this is the beta pocket. I'm showing you all this basically to establish that these samples, this is very consistent across ARPES and SDM. Okay, so now we can turn on a magnetic field and look for these Majorana bound states. And so here's a DIDV map showing vortices. You can almost see a hexagonal arrangement of the vortices here. And if you look at one of these vortices, take a line cut across it, here's what you see. Here's the superconducting gap far away. And right at the center of the vortex core, you see a nice sharp peak in the density of states that's at 0 energy. Now, the first people to look at vortices in this system were Hong Ding and, sorry about that, Hong Jun Gao. They did some really nice work showing for the first time that you see the 0 bias vortex in this material. The problem is that at the beginning, when this work was done around 2018, they found that only a small fraction of the vortices would show these 0 bias states. So there was that problem. And then one can ask, okay, you can see 0 bias states. You actually see 0 bias vortex core states even in niobium diselenide. The question is, what is the proof that these are actually Majorana bound states? In fact, one knows that you should see Carolyi-Dijon metricon bound states, which are just regular bound states inside a vortex core, even for an ordinary superconductor. Now you can ask the question, how do you distinguish these Carolyi-Dijon metricon bound states from Majorana bound states? And the answer is that the energy of these trivial vortex core states is given by this, where delta is the superconducting gap and this is the Fermi energy. Now, if you think about the surface state of that we see in FESET, the Fermi energy is less than 10 millivolts, and the superconducting gap is around 1.5 MeV. And if you plug these numbers in, you realize that the trivial bound states should have energy scales of about 100 microvolts, which is actually pretty large for SDM at low temperatures. So this is work done by Hanaguri's group. This is really beautiful, detailed work. And he shows many things quite clearly. One of the things he could do, because he could go to really low temperatures, is he could show that there are 0 bias bound states which are well within the energy, the energy resolution is good enough to say that these are well within this 100 microvolts. In fact, they're probably, exactly centered at the Fermi energy. So that's pretty good proof that these are Majorana bound states. Interestingly, if you're interested in this vortex work, you can also see that what he shows is that if you go to very low magnetic fields, a much larger percentage of the vortices show 0 bias states. And as you increase the magnetic field, the number of 0 bias states actually goes down quite dramatically. More recently, Hong Ding and Hong Jun Gao have done actually 2 important pieces of work on these vortex bound states. One is that they've shown that you can have, unlike the trivial Carolyi-Metricon Dijon states, you can have vortices where you have integer spacing between the vortex bound states, and this is consistent with this being Majorana fermions. Another thing they showed is that you can show that the DIDV saturates to a value of E squared over H only for these zero bias states and not for the trivial states. And so all of this together suggests pretty strongly that one can see, these zero bias states seen in FESCTE are in fact Majorana modes. Now, in my lab, when we started looking at FESCTE, we were interested in, this was a while ago that we were interested in this. And at that point, there was, these pieces of evidence were not there. So we were very interested in asking the question, can we find any other evidence that this material is topologically non-trivial? So one thing you can do is look for signatures of these propagating Majorana states. And we have superconductivity. We know this is topologically non-trivial, at least now we do. I think there's enough evidence. The third ingredient you need is a pi phase shift. So as it turns out, this FESCTE is really intriguing because Jianping Hu wrote a paper in 2013 where he showed that if you consider all the important interactions, nearest neighbor, next nearest neighbor, and so on, then what you find is a very interesting kind of superconductor where, so this is one of the layers. This could be Fe arsenic and arsenic, or iron selenium selenium. But in any case, what you find is that the sign of the order parameter switches from the top to the bottom layer. So there's a pi phase shift in the sign of the order parameter between the top and the bottom selenium or arsenic layers. So this would be very hard to probe unless you looked at a monolayer. However, one interesting thing about this idea is that if you could find a sort of a domain wall in the system where the top and bottom seleniums are flipped, and this is what I was talking about at the beginning of the talk, you should actually expect to see these kinds of domain walls, then you naturally have a pi phase shift in the superconducting order parameter. So here's the idea. So this is the top view on one side of the domain wall. These are the top selenium atoms. And then on the other side of the domain wall, the crystal has simply flipped over. So then what you expect to see is a half unit cell shift of the top atoms. So these, you see, this is the top atoms here, and these are the top atoms here. This is the domain wall. So you expect to see a half unit cell shift. And if you can find such a domain wall, then at least theoretically, you have all the ingredients necessary to realize propagating Majorana fermions. So, the samples normally look like this. You don't see any signs of domain walls, but if you search around, you can also see regions like this, where you have these long lines. And not all of these lines are domain walls, but if you search around long enough, then you can find the right kind of domain wall that we're looking for. So one thing is you take a region, a topography like this, and you do a Fourier transform, you immediately see that, if you zoom in here, this is the atomic lattice. And the fact is that you have these two dots. The presence of a split peak in the Fourier transform indicates that there's these two sides are actually two different domains. It doesn't tell you there's a pi phase shift. To see that the atoms are shifted by half a unit cell, you have to zoom in, and you can either track the atoms with by drawing lines, which is a pretty crude technique. But we've also done a more serious analysis using the phase and the Fourier transform. But essentially, whatever method you use, you can show that the atoms on the left side of this domain wall are shifted from the atoms on the right side of the domain wall by exactly half a unit cell. So this is exactly the kind of domain wall we're interested in. So then now we can ask, what do we see when we go to such a domain wall? And so here's what we see. So far away from the domain wall, we see a nice superconducting gap with actually 0 density of states. And if you go to the domain wall, you see the gap, but then you see this flat density of states inside the superconducting gap. So the superconducting gap is filled up. You know, you have a finite density of states, but it's a flat density of states. So you can, so here is more data. So this is a line cut, which goes this way and then this way. So when you go in this direction, you see the nice superconducting gap, meaning the density of states is suppressed. And when you go along the domain wall, you see very featureless density of states inside the superconducting gap. Then you can actually increase temperature and make sure that this feature is associated with superconductivity. So this is on the domain wall. This is the spectrum on the domain wall showing the finite density of states. And if you go to high temperatures, which is 14 Kelvin above TC, this entire feature disappears. Okay, so why do you get this flat density of states? Actually, the answer is quite simple. What is predicted in the system is that you should see linearly dispersing helical states inside the superconducting gap. And if you ask what is the density of states of a one-dimensional linearly dispersing mode, it's constant. So that's exactly why you see this constant density of states. So this constant density of states represents a linearly dispersing mode living inside the superconducting gap. And then you can do other checks. This is just one example of a check. So you can take density of states maps as a function of energy. So right at 0 bias, this is the domain wall. You can see that at 0 bias, you have a nicely confined state living exactly in the region of the domain wall. As you increase energy, the width of the state, the spatial extent actually increases. And by the time you get to 1 millivolt, it's actually spanned, it basically fills up the entire field of view. So this is exactly what you would expect for a topological state, because for a topological state, what you expect is that you should see states at all energies inside the gap, but the spatial extent of the state should increase as you get further and further away from 0. Okay, so I think that, so these are the two things I wanted to show you. There's been a lot of work done by many different groups showing 0 bias bound states inside vortex cores in this compound. And what we've shown is that if you find the right kind of domain wall in the system, you can get propagating Majorana modes. So I'm just going to, since I started late, Ming, how much time do I have? Another 5 minutes?
Well, yeah, go ahead. Maybe not 5 minutes, but yeah, it's obviously off the time, but I think, yeah, you can.
Right. No, when did I start? Okay, I don't know when I started. Shall I just flash some slides? I just wanted to flash a couple of slides and then
yeah, go ahead.
Okay, so just want to show you something really interesting. This was Jianping Hu's prediction that if you have, for these ion-based compounds, we know there's a lot of evidence that we have an S plus minus order parameter, where the order parameter has a phase shift between the electron and the hole pockets. But if what he predicts is correct, which is what we based our analysis on, you also expect to see a pi phase shift between the two hole pockets at the gamma point. So we wanted to try to grow monolayers of FeSET on bismuth selenide for various reasons. And I don't know if I'm going to have time to go through this whole thing, but let me just show you a few slides because this is very interesting. So we used our MBE system to grow FeSETE on bismuth telluride. So here's bismuth telluride, right? And here's FeSETE. And so you can see very clearly, so this is the hexagonal lattice associated with bismuth telluride, and this is one monolayer of FeSET. Now, this is pretty crazy. You don't know if this is superconducting at all. If it is superconducting, you don't know what the TC is, etc. But I'll show you that this thing is indeed superconducting. Let me skip all this. So, okay. So this is the FeSET layer. This is bismuth telluride. And if you go in here and take a series of spectra, this is what it looks like. The important thing here to notice is that this gap looks exactly like the gap we saw in the bulk compound. By the way, this topography should remind you of the bulk compound. You see 3 distinct gaps with, if some regions have very nice sharp coherence peaks. But the most important thing is that the density of states is actually complete, like 0 inside the superconducting gap. So this monolayer of FeSET on bismuth telluride is a very, very good superconductor. And the TC is very similar to the bulk. So, by 13 Kelvin, that's when the gap completely disappears. You can see this proximity effect. The proximity effect is really interesting. This is bismuth telluride. And what you see is that you see a shallow gap on bismuth telluride. Remember, this is lateral proximity effect. So one imagines that only the surface state is getting proximatized. There's also the gap magnitude is pretty small compared to the gap magnitude on FeSET. But in the interest of time, I'm going to skip over all this and just show you one interesting thing, which is that with STM, you can do a phase analysis and you can ask the question, what is the relative phase of the autoparameter in these various pockets? And by doing this phase analysis, what we found is that not only is there a phase shift between the hole pockets and the electron pockets, but there's also a relative phase shift between the 2 hole pockets at the gamma point, which is very much in line with Jianping-Hu's prediction. Okay, I'm going to just stop here because I think I've run out of time. Thank you for your attention.
Thank you very much, Vidya, for this very intriguing talk. Any questions from the audience?
Shall I stop sharing or shall I keep sharing?
I think sharing is okay. So we have a question from Andrei Nemdovsky. Andrei, do you want to ask your question?
Yeah, sure. Hi, Vidya. Thanks for a very, very nice talk. I had a question about maybe the last part of the talk. Could you reflect on what you just told us about this relative sign change and the proposal that if you have a FeSE, this S plus minus superconducting this material, then our proposal this might actually be a higher order topological superconductor. So if you imagine making like a parallel pipe out of it, like you just think of a cube, then the gapless modes would naturally exist on the hinges of this cube. And so Nick Butch, for instance, took it as far as to then try to create a sort of nanolithographic device and measure the DIDV. And the statement or the claim is that the zero bias peak that he sees is exactly coming from these hinge modes that live sort of on the edge, if you see my hand, sort of on the edge of the two faces of the cube. So is this in any way related to Jianping-Hu's proposal and the kind of features you are looking for?
So there are 2 things. One is okay, so yeah, I know what you're talking about. Let me think for 1 second. So the Jianping-Hu's idea that if you take into account all the nearest neighbor, next nearest neighbor hoppings, etc., that it's this so-called effectively an odd parity superconductor. Can you see my screen?
Not a full screen, but we can see it, yeah.
Yeah, okay. So this is Jianping-Hu's proposal. I think this is consistent with the existence of hinge modes. If you have a 90-degree, if you have a sort of a crystal facet, this going this way and this way, I think this would also give you edge modes, actually. Yeah.
Well, just to be clear, Jianping-Hu's proposal is about the right-hand side, not the left-hand side of the figure, right? I think the left-hand side is just for comparison. What would happen in putative P-wave superconductor?
No, actually, the left is Jianping-Hu's proposal. And the right is what, so this is what he's proposing. This is, I couldn't change this. This is directly taken from his talk, but I would have put quotes around the odd parity. So this is an effective odd parity superconductor is what he's proposing. Not just FeSET, depending upon the circumstances. He's saying many of the pnictide compounds could be in this particular state where if you do realize this kind of effective odd parity superconductor, then the proposal would be that not only do you have a sign change in the order parameter between the hole and the electron pockets as shown here on the right, but you also have a sign change between the two hole pockets themselves. And this also is the reason that you would then, let me see, this is the same idea that where you have the superconducting order parameter then having, having the top layer and the bottom layer also show, in real space, also show a phase shift. So those two things go hand in hand.
I see. Very good.
Thank you. And next question, Amir.
Yeah, thank you very much for your very nice talk. I have a question regarding the growth of this iron selenium tellurium 50-50. You said that you can grow these materials without interstitials or iron excess.
Yeah.
And yeah, I find it a bit strange because that material actually allows iron excess in the lattice, and normally the people, they anneal the samples, and still if you anneal it, it's not guaranteed that it's not 100% of
you're absolutely
the
right.
iron, exactly, the excess of iron. So I'm puzzled by the fact of, also from the phase diagram point of view, it's a little bit surprising to me that one can access it. I mean,
there's a reason. I can tell you the reason.
Yeah, go ahead.
Okay, the reason is the way we grow it. It's iron deficient in some ways. So what we do is it's a clever technique, actually. We didn't invent this. You put iron on top of bismuth telluride, okay? And just iron, right? And you anneal it in a selenium atmosphere. And so all the iron that exists on top, it binds to either selenium or tellurium. That's why you end up with no excess iron. So the way you grow this is not what we're not growing it by evaporating Fe, Se, and Te. Instead, we're depositing only iron on top of bismuth telluride, and then annealing in a selenium-rich atmosphere, and that's it. And that's what gives you this. So the proof of the pudding, I mean, the thing is that you do that, and this is what you end up with. You don't end up with any excess iron. It's really nice.
Okay, thank you very much.
Sure.
And last question, Sunil.
Yeah, really a beautiful talk. So I actually have a question which maybe more is for ARPA's groups, but in a spirit of discussion.
Yeah.
How much of the evidence that there actually is for the band inversion in a bulk?
Yeah, okay. This is very tricky. So when this paper was first published, Hongding's paper, I think there was a lot of controversy. I'm not sure everyone believed it. And we ourselves were extremely skeptical. And the one reason that I wanted to actually study this compound was because I wasn't convinced at all by this RPAS. However, there are two things. One is, I think multiple groups have seen these surface states now. So there's that. And you can show that they're surface states because, there's no KZ dispersion. Moreover, I think that's what I meant by accumulating data. I think that given all the beautiful work done by Hongding, Hongjun Gao, and Hanaguri, showing that these Majorana bound states exist inside the vortex cores in these compounds, you might think of it as indirect evidence. But I think that without a topological surface state, that would not happen. So if you have, so just working backwards, you have Majorana bound states that requires a topological surface state, which in turn requires band inversion at an odd number of points inside the Brillouin zone. So that's my answer.
No, that's fair. But on the other hand, this is the material which has been looked at from a variety of perspectives, including from correlation physics and etc. So there's a lot of ARPAS data that probes the bulk spectrum. And I just wonder whether anybody has really directly seen the inversion of the P and D bands in the bulk.
You want to do this as a function of doping, I presume?
No, just 50-50. And
if I may comment, this was just done. I posted the link to the archive paper. So there is a appearance of the topological surface state as a function of tellurium concentration and disappearance of superconductivity.
No, but I'm asking about a bulk, not a surface state.
Yeah, there is appearance of a surface state which is indicative of a band inversion in the bulk. And there is that's as a function of tellurium. It actually happens not at 50%, but around 55.
Yeah.
So there is a phase diagram that has been recently established of topological superconductivity, non-topological superconductivity, and in fact, the non-superconducting state at the excess of iron, which begins roughly at a stoichiometric composition of iron 1. So this phase diagram is basically similar to the famous phase diagram of correlated materials in strong spin orbit regime. So X, the iron composition, quantifies the correlation effect, and Y, the tellurium composition, quantifies the strong spin orbit coupling effect. So in any case, what I wanted to mention is that in the real material, of course, you have fluctuations of composition. So there are regions from different parts of that phase diagram. And the reason that people have observed topological and non-topological vortices at the same time on the surface of the same sample is because these gathered samples, which are 0.45, 0.55, are nearly exactly at the boundary of the non-topological to topological superconductivity transition.
So I can pull up the paper, but I don't think we have time. Yeah. What is the...
That's it. I mean, you can look it up. Figure 4 shows the phase diagram I was talking about.
Okay, all right.
Sounds like this would be a good topic.
I think we should probably stop on this point. But the point is that at least according to DFT, the banding inversion is actually happening above the Fermi energy. So I don't know how ARPAS can actually see it.
Sounds like it's a topic we can follow up with the discussion.
No, that's true. So that there is that problem. Maybe I should stop talking because Ming wants me to, but there is that problem. Band inversion is not happening. Yeah, band inversion is happening at a different point in KZ. That's true. That's why you can only see it indirectly. If a surface state suddenly appears and it has sort of linear dispersion, then you have to ask, why is there a surface state now suddenly at this composition?
Thank you, Vidya.
So the surface state, I think various ARPAS group have seen with laser ARPAS where you have the resolution to see the surface state. But I guess the question is, can you do this with KZ dependence at a synchrotron? And that's something I think a number of groups are working on. Perhaps that will contribute to this discussion.
Mm-hmm. Okay, I'm going to stop sharing.
Thank you very much, Vidya, for this very interesting discussion. Maybe we can follow up in the discussion tomorrow, since we have one more talk by Ziqiang Wang from Boston College. Ziqiang, do you want to start sharing your screen? Are you there?
Okay, yeah, I'm here. Can you see the screen?
Yes. You want to try to share? Perfect.
Oh,
Yeah.
okay. All right. So I'm going to the beginning. All right.
Sure.
So I'd like to begin by thanking the organizers for such a wonderful symposium during such a difficult period of time and for giving me a chance to speak. So the work I'll be talking about, the theory part, was done in collaboration with my former graduate student postdoc, who is now at IOP, Kun Jiang, and Shi Dai, who is on his way from Hong Kong University of Science and Technology to UCSB. And we've collaborated with various experimental groups that I won't go through each individually. So my plan is the following. I'll explain what is a quantum anomalous vortex and how it came to light in the search for Majorana zero modes, vortex Majorana zero modes in ion-based superconductors. And after I accomplish that, which I hope within the time limit I can, I'll describe some new experiments and theories that really put additional evidence for finding the quantum anomalous vortex. So what is a quantum anomalous vortex? If we put a magnetic impurity in a superconductor, the breaking of time reversal symmetry will cause the Yushaba-Rosenov states to appear. However, these are not vortices, and to have a vortex in a type 2 superconductor, you need an external magnetic field. So what we found is this conventional folklore changes in a fundamental way in a S-wave superconductor, let's say with strong spin-orbit coupling. In that case, if you put a magnetic impurity in the superconductor, there will be a spontaneous quantized phase winding develops in the superconducting order parameter, and therefore a spontaneous vortex, if you wish, of the supercurrent without applying external magnetic field. And the role of the magnetic field is played by the spin orbital exchange field. And we call such vortices quantum anomalous vortex. And it is, in fact, formally speaking, a superconducting analog of the quantum anomalous Hall effect, in which you take a topological insulator thin film and dope with magnetic ions and produce a quantum anomalous Hall state without external magnetic field. So the quantum anomalous vortex per se has nothing to do with Majorana zero mode. However, it came to light because of the search for Majorana zero modes in ion-based superconductors. So let me begin immediately with what is a vortex excitation in a type 2 superconductor and what are vortex core states. And here I have a vortex which is a deformation of both of the amplitude to 0 of the pairing field, and then a quantized phase winding around it, so that I have a circulating supercurrent around the vortex. And in the vortex, I have the vortex core states. Now, Carulli, Dijay, and Matricon did the calculation and showed that these vortex core states are quantized, and they're quantized by half-odd integers. And it's very easy to understand this half-odd integer, because if you take a particle and go around the vortex, you pick up an angular quantum number that is the angular momentum quantum number and plus half of the vorticity. And that's why it's always half-odd integer. And in particular, it does not include the zero energy state. And these are observed, of course, in niobium diselenide, where this is a curve away from the vortex. And as you go to the center of the vortex, you see this vortex core states. It's important to know that niobium diselenide is in the BCS limit. That is, the gap is much less than the Fermi energy. So these in-gap states are actually continuous. And this is a very nice calculation done by Bardeen, and it's a very interesting paper to read, where he calculated these states and showed that it is a continuous states, interpolating between one gap and the other gap. That's why you see this. Now, in order to really see the discretized states, you need to go to the quantum limit of a superconductor. That is a superconductor with its gap comparable to Fermi energy. In this case, you see the discretized quantized states, but none of them is at zero energy. And we know if we had one at zero energy, we would have this Majorana zero mode. So how do we generate a vortex Majorana zero mode? And that is how to generate a non-abelian vortex. And if you look at the quantization condition here, you know you have to turn this quantization condition from half integer to integer. And in order to do that, you need an extra phase that I call eta here. Imagine I can do that. Then the core energy would be quantized by an integer. So it would start with 0 plus minus 1 and all that. And therefore, the one that sits at 0 with the quantum number mu here equal to 0 is the Majorana zero mode, which is a pair of degenerate states that appears at the ends of the vortex line. So the question is how to get this extra phase, eta. And obviously, if you think about it, it's easy to convince yourself there are two ways. One is to get this eta from the pairs themselves, and that is path A. You get eta equals to 1 from a chiral P plus IP topological superconductor or superfluid. This is the proposal of Reed and Green. And nature hasn't been kind to us. There are very few even candidate P plus IP topological superconductors. But there is a path B. The path B is to get this eta not from the pairs, but from the particle Hall sector, that is through the Berry phase of the helical Dirac fermions. So if I write the Dirac equation on curved space, such as I take a disk, and you see there is this phase, this wonderful phase factor coming out, and that's the spin-Berry phase. And that adds this half angular momentum in each of the spin species. So even in the normal state, now, if I take a particle going around the origin, I would pick up a half integer quantization. Now, if I make the Dirac fermion superconductor, and then look at the vortex core, this is this -1 here that came from the Berry phase is exactly the eta I needed to make this angular momentum quantum number to be integer. And in this case, I would have a vortex core states, a sequence of vortex core states that are integer quantized and include the zero mode. And that's the Majorana zero mode. So in this sense, the S-wave pairing of helical Dirac fermions will do. And this is indeed what's behind the proposal of Fu and Kane that Vidya just talked about. You need a 3D strong TI with topological surface states, the helical Dirac cone, proximity effect coupled to a S-wave superconductor, and that will present to you a zero energy state as a vortex core state. However, this discussion also motivates a general perspective of these physics, is that what we need really is one superconductor. We don't need a hybrid structure. But this one superconductor should have a topological, a Z2 topological band structure. So therefore, your starting point should be a Z2 topological metal. That is to say, maybe a doped topological insulator. So both the bulk bands and the surface states are doped. Now, if you manage to make this guy superconducting, you would gap the bulk states, and you would necessarily induce a paired states on the surface state, on the topological surface state. So this is a way of achieving a superconducting topological surface state. And once you have that, you have vortex Majorana zero mode. So I want to emphasize that this is by no means a topological superconductor, not in the sense of the usual definition that we have for topological superconductor to have a non-trivial topological invariant. It is not that. It is an S-wave superconductor, but the topological aspect comes from the band structure. Okay. Now, FTS really is such a candidate. It's a Z2. It has a Z2 topological band structure. And I want to emphasize the reason for this to happen is because, well, one can ask, why does it happen in ion-based superconductors? Or various reasons, but one of the most, I think, basic reason is that ion-based superconductors are PD charge transfer metals as opposed to cuprates, which are PD charge transfer insulators. So the p bands are close to the Fermi level. And in FE, TE, SE, the tellurium atoms are big. So they hybridize, the pz orbitals between different surfaces really strongly hybridize. This pushes the pz orbital further down towards the Fermi level, and therefore it crosses the d bands, and of course crosses the Fermi level. So this causes a band inversion of odd parity pz and dxz band, and the SOC spin orbit coupling will then create a gap along the gamma z direction. And this non-trivial Z2 invariant is the origin for generating topological surface states. But of course, this thing is doped. It's not exactly an insulator. So the normal state can be thought as a strong Z2 topological metal. And there is a single Dirac cone on the 001 Fermi surface. I said this very cavalierly. In fact, there is not a theory, a real theory that can produce all of this. The LDA calculation give you something that is a bit off from this picture. Of course, we would assume that perhaps the correlation effects that are so important in the chalcogenides, that causes the renormalization of the bands that brings the FDA band, LDA band structure to this one. That's what's measured experimentally. Okay, so now to go from that kind of understanding to actually observe these things in theory, you really would have to have all the stars line up and everything, but they did happen. This is the work that Vidya mentioned by Pen Zhan, who is going to be talking tonight. And this is a groundbreaking work in my view, that they use spin polarized RPES with very high resolution and directly observe the Dirac cone topological surface states with spin orbit helicity. Now, everything that they found is actually peculiar of FETE-SE, which played a role in what I'm going to say later. The Dirac cone is about 5 millivolts below the Fermi level. And in fact, the bulk band has a tiny Fermi energy, 4.5 millieV of this whole band. Now, if they go below TC, they found that there is a gap, superconducting gap developing in the topological surface states. And that's a reason, I think that's evidence that we have for this new quantum state of matter, which is the superconducting topological surface states. Once again, this is not a topological superconductor. My experimental colleagues are very excited and wanting to call this thing a topological superconductor. It might be in some higher order categories, higher order definitions, but not in the conventional sense. But nevertheless, our discussion tells us if we apply a magnetic field, we should see Majorana zero mode in the vortex core because of these superconducting topological surface states. And that indeed has been found. FTS, you see the zero energy bound state, and that is a candidate Majorana zero mode. And later on, Hanaguri's group has this ultra high resolution measurements that makes it even more convincing. Of course, there are both vortices with and vortices without the zero energy mode. You can think of this as having both abelian and non-abelian vortices coexisting because of the inhomogeneity of the surface. Now, this is quite universal. I don't want to make a point that this is not just in FTS. This is FESE. FESE by itself doesn't have surface state, but if you interpolate this way, you get topological surface state. And then in the vortex, you see the zero energy bound state. And it's even in the pnictides. Again, this is also something I think, is it Vidya? Or no, the first talk this morning also mentioned this pnictides, this 1144, which is a bilayer ion pnictides that has surface states. And very recently, they have observed also this zero energy bound state in the vortex core. So all of these are actually, if so far, the criteria, which is a poor criteria, but it certainly is the first criteria, first step is to see the zero energy bound state in STM. But however, the very first observation of a robust zero energy bound state in FETSE was actually made on top of access ions and was actually made about 3 years early in 2015. So the access ions in FETSE are very well known. They are as grown. And they sit at the C4 symmetric sites, which is in the middle between 4 tellurium and selenium atoms here. And neutron scattering studied this very carefully early on. The ion carries a spin orbit moment of about 2.5 Bohr magneton and points along the z-axis due to magnetic anisotropy. And they're not ordered, they're disordered. And the neutron scattering actually find they survive in the superconducting state and may have some coexistence of magnetic polarons in the superconducting state. Okay, so 2015, we thought with STM, this is in collaboration with Shu Han's group, we would just tunnel into these excess ions. The idea was to see if this will tell us something about the nature of the pairing or the superconducting order parameter. But we found something quite astonishing. And this is the STM curve. If you go away from this excess ion, you have a flat bottom S-wave superconductor. But if you come to the ion, the excess ion, you see a zero energy peak. In fact, this is a zoomed in picture. This is a robust zero energy peak that only sets in below superconducting transition. And it's robust against the magnetic field. And there are even other evidence that tells us this is not a usual magnetic impurity state. It's got a kind of topological origin. And is in fact, if you look at all the spectroscopy properties of this zero energy state, it is consistent with a Majorana zero mode, but in zero magnetic field. Here I show this again. I want to actually make a point. If you look at Shu Han's data, this is a V-shaped density of states at -5 millieV. And that is completely consistent with RPES having a Dirac crossing about 5 millivolts below the Fermi level. So this is indeed what's seen here is a superconducting topological surface state. But how would we have a zero bias peak or zero energy bound state in zero magnetic field? And in fact, this reminds us of the famous quote by Rabi when muon was discovered instead of the anticipated mesons. Who ordered that? And in particular, is this really a bona fide Majorana zero mode? So now our proposal is what I described in the very beginning, that there is a quantum anomalous vortex, a vortex in zero magnetic field that nucleates spontaneously around the interstitial magnetic ion without external magnetic field. And that hosts a Majorana zero mode from the superconducting topological surface state. So we need to, of course, do a calculation to show that indeed, in this case, it's better to have a vortex instead of a vortex-free Yeshiva state. And that I won't have time to describe in detail, but I can show you. So I can sketch the philosophy is the red line is the whole band around gamma point, the bulk band. The blue one is the surface state. To get QAV, the quantum anomalous vortex, we work with the bulk bands, not the superconducting topological surface state. And we took parameters from RPES. And of course, the magnetic ion is put there with a exchange coupling to the total angular momentum of the quasi-particle. And we do the whole thing on the disk by solving the BDG equation in the presence of a vortex. Now, a few words about the energy cost of the vortices. Basically, the main parts are two contributions. The core energy, which is really the penalty you pay for creating a vortex. And also there is a vortex line tension, which is the line energy. And you can estimate this for FETSE. Here this is just BCS estimates, but you have experimental parameters. The main point I want to point out is the line tension is a function of E squared over delta. So being in the extreme quantum limit for FTS tells you that this number you can get is 2.5 millieV per coherence length. So the line tension is very small. So the vortices are very floppy. They're easy to bend, to manipulate. And if you did the same thing for cuprates, you get something on the order of 800 millieV. Okay. Now, the second thing, of course, is the core energy. The core energy is what you pay usually, but because of the strong spin-orbit coupling, you actually gain this energy. This is what gives the Lorentz force. And you can estimate this because we know the total angular momentum of an elemental vortex is the number of pairs times h bar. And now you can estimate the energy from the binding part. Now, when these two become comparable, you have a quantum anomalous vortex nucleation. So now when the binding energy becomes larger than the line energy, you get this equation. And for short-range exchange field, you see that all you need is the exchange coupling to be greater than the Fermi energy. And the very small Fermi energy, 4.5 millivolts for FTS, is what's favoring this quantum anomalous vortex. And this is a complete numerical calculation. Here we plot this binding energy as a function of the exchange field. On this side, you have the Yushiba vortex-free states. But when the exchange coupling becomes stronger, larger than the Fermi energy, you have a quantum anomalous vortex spontaneous nucleation. In fact, there is a transition now going from Yushiba states to a vortex state. Okay, and now once we have the vortex, of course, we just couple that to the superconducting topological surface state. That is the blue line. Now you got the extra Barry phase. You get zero mode, integer quantized core states with the zero mode. But for this set of parameters, the core states are clear from are cleared up from the vortex core, and that gives rise to this very robust zero energy peak, and that compares very well to Schuhan's experiment. Okay, so if we have dilute magnetic ions, what we really have here is the emergence of quantum anomalous vortex anti-vortex matter at zero temperature. These are quantum phenomena, and with zero external magnetic field, which might be a better platform or more advantageous platform because we have a single material, no external magnetic field, and presumably, or at least in principle, you can manipulate these ions to achieve manipulation of Majorana zero mode. So in the next 5 minutes, I'm going to turn around and show some new results by focusing on 2 points. The first one is, how general is this phenomena? If this is true in this as-grown FTS with excess ions, then if I just spray the surface with magnetic odd atoms, I should see this. That's one thing. The other thing I want to talk about is, in addition to this zero energy peak, which seems to be the only experimental phenomena as of now, can you see more things to indicate that the quantum anomalous vortex indeed exists? I will do these 2 things. So I go rather quickly. This is from Princeton's group. They did atomic deposition of ion atoms on lithium-111, which has been talked about quite a bit at the symposium. 111 has a Z2 topological band structure. In fact, yesterday we heard it's actually quite intriguing. And Hanaguri did the vortex measurement quite early on. And the blue line is away from the vortex, and the red one is on the vortex, at the vortex, in the vortex center. You don't see a zero bias peak. In fact, the vortex seems to be gapless. So because of the Z2 topological band structure is quite non-trivial, the vortices from the superconducting topological surface states are actually highly non-trivial here. Now, when they put the odd atom ion on top of lithium-111, they see that the vortices actually get cleared up. And you see this zero energy peak at 8 of the 27, I think, access ions they looked at. They're at zero energy. And it may indicate that the exchange coupling can actually clear out these gapless states in the vortex in the absence of the magnetic ion. Now, more recently, the Hong Jungao and Hong Ding's group at IOP deposited magnetic ions on the surface of FTS. Now, this is quite spectacular because now we see 2 kinds of odd atom ions. There is what I call type 1 here that shows a zero energy peak, just like what we would anticipate from a QAV nucleated at the magnetic ion. We also see type 2 atom ions. These guys show Ueshiba states, right? No zero energy peak. This is actually parallel to what you see in adding a magnetic field. You see both topological vortices and non-topological vortices. Okay, so a closer look at this shows that the type 1 atom ions will have this zero energy bound state. What's really interesting is if you do a map of the zero energy state, you see this candidate Majorana zero mode peaks away from the magnetic ion, which is a little circle. So this off-centered Majorana modes, I'll come back in a bit to explain. And these other type 2, if you add a magnetic field, they actually split. So giving you a G factor about 0.9, very reasonable. So it's comforting to see both. You do see Ueshiba states, and you also see zero energy mode, presumably due to the vortices induced. Now, this sample is always inhomogeneous. So the trick is to collapse all of these waterfall plot onto a single plot. You see, in addition to a zero energy bound state, you see also other states. And if you look at these states, they are integer quantized. And in fact, it's about 1 millivolts times an integer, including 0. So this is really concrete, I would say, one more evidence that indeed the ion induced a vortex, because you see the vortex states. And in fact, you compare this to a magnetic field induced vortex, where also these vortex core states are seen. And that's 0.6 times the integer. So you really just increase the mini gap of the vortex state by a factor of 2. And they're completely analogous one another. So therefore, I hope this proves there's a dual origin of the vortices and vortex Majorana zero modes in ion-based superconductors with topological surface states. They can be induced by magnetic field or by magnetic impurity. And I won't have time to say this, but I'm just going to flash this. They could actually use the tip to turn an ion impurity that only shows Ueshiba states, and you can push it in so that the state collapses and turns into a single zero energy state. And this is a transition. In fact, it's also reversible from Ueshiba to the quantum anomalous vortex state. And there is also initial data for observing the interaction of a quantum anomalous vortex-induced Majorana zero mode and a B-field-induced zero mode. As you see here, this is a impurity-induced zero mode. And a vortex creeps in if you put this thing in the magnetic field. And these two things fuse, you lose the zero energy state. And if you wait, this vortex hops away, the field-induced vortex, they move, it hops away, and you recover what you had before. Okay, now let me just explain why the Majorana zero mode can be off-centered. And that is because the impurity of the moment of the impurity spin could be canted away from the surface normal. Impurity center because of the breaking of the rotation symmetry. And that kind of accounts for the experimental observation. An immediate consequence of this is if you then calculate the current distribution, you find that a magnetic QAV in general can be a dipole, can have a dipole structure. In other words, if you calculate the magnetic field, on this side is pointing, let's say, up or down, and on the other side it points in the opposite way. So the Z direction B field distribution is that of a dipole. Okay, now I'm coming to my last transparency. It was really exciting in the last couple of months. The group of Yihua Wang at Fudan University, they have the ability of doing scanning squid measurement. And so they are able to actually see these vortices directly, because that's the only, I think, sort of necessary condition for you to claim there is actually vortices in this case. I'm just going to briefly flash these data. This is the diamagnetic susceptibility. You see the sample, which is a FESE TE flake. And then here, the squid coil will pick up the magnetic flux. The center 3 are zero field cooled, and they have to do a lot of experiment to make sure there are no magnetic field around. And you see different zero field cooling will give you these vortex anti-vortex pairs in zero magnetic field. And it's actually a stochastic phenomena because at different times, you might nucleate these things at different ion impurities. And if you do this in the field, of course, you have vortex or anomalous vortex. Now, this phenomena is not seen if you use FESE. It's also not seen if you use niobium, a standard BCS superconductor, which they actually showed in this wonderful plot. That if you first look at the stars, which is from a niobium film, when you have no applied field or small applied field, you have no vortices. Right? You need a threshold, HC1, to actually see these things coming in for niobium. Now, the circles are for FTS. You do not need any external field, and they nucleate along the zero field line. And for small field, you have both vortices and anti-vortices. And of course, when the field becomes strong, you have predominant vortex or anti-vortex. And the magnetic field distribution going along a vortex anti-vortex pair is shown here, which indeed exhibit this dipolar character of a quantum anomalous vortex when the magnetic moment of the magnetic ions are canted away from the vortices. So that's all I have to present today. And I'm going to just put up the summary sheet. And there are a few things I didn't say. This quantum anomalous vortex, spontaneous or nucleated vortices and magnetic impurities should appear also in topological superconductors if we had one, right? And there are things I haven't mentioned, that these Marana or zero energy bound state tied to quantum anomalous vortices are indeed seen at ion add atoms in monolayer FETESE and FESE field. And also more recently, in monolayer FETESE, along a atomic line defect, there are zero energy bound state appearing at both ends of this atomic line defects, which is really saying that we can engineering or putting quantum structures, embedded quantum structures in FTS and observe true topological superconductors in reduced dimension. And more recently, there are also spontaneous Lorentz effect observed in bulk FTS. That can be explained as due to quantum anomalous vortices induced by access ions. So I will stop here and thank you for your attention.
Thank you very much, Tom, for this really rich talk. I see a hand raised by Andre.
Yes, Ming. Right. Zichang, I have a question about the energetics.
Okay.
So you've argued that fundamentally the reason why the quantum anomalous vortex would exist is because it preferentially would bind to a local add atom site, and the energy of nucleating that vortex exceeds the line tension, right?
Yes.
In 3D.
Yes.
Now, why would you have two kinds of add atoms? I mean, on the surface of it, the only difference, I mean, the parameter that you care about is the ratio of something like EF squared over delta, right?
Excellent.
So, for a given material, Fermi energy is fixed. So why on the surface of, let's say, lithium-ion arsenic, would you have two kind of add atoms?
Yeah, excellent question. In fact, it's the same question that one could ask, why do you have two kinds of vortices? I know there are, in magnetic field induced vortex, some of them have zero bias peaks and some of them don't. And there are many ways they try to explain this. They meaning various groups trying to explain this. But the most, I think, convincing explanation is because of the surface inhomogeneity due to the alloying. Some parts may have topological surface states. Other parts may have a void or a different kind of surface state with different chemical potential. So therefore, you can think the type 1 ion atom sits in a region where there are topological, well-defined topological surface states with low chemical potential. You know, when the chemical potential is too high, the topological property is gone. And the type 2 odd atom sits in the region where the surface states are very nicely protected. They're just like what's been observed by RPES.
I see. And just to, sorry, just to, if I understood correctly, please correct me if I'm wrong. I'm trying to get sort of a two-sentence summary of what you said, which is which was a lot of material. But in the first part of the talk, you argued that there's an non-abelian vortices, the one that give you topologically non-trivial zero-bound Majorana states. In the first part of the talk, they come from the underlying Z2 invariant of the topology of the bands, correct?
Yeah.
The second part of the talk, you said, well, forget about the topology. Even if somebody gives you a plain vanilla superconductor like lithium-ion arsenic, if you imagine putting add atoms with strong enough spin-orbit coupling, you could have either Yi-Shiba-Rusinov states, or you could have this other non-abelian states. And
Yes.
which one wins depends on energetics. And hey, it's possible that even in the same sample, you might have both. Is that
Yes.
a fair representation?
That's a fair statement. In fact, the best would be, most convincing thing would be not to bother with the zero energy mode, but take a conventional superconductor that is not even, well, what we need is a superconductor that has strong spin orbit coupling. Right. Then you know that it's going to have some sort of a Z2 band structure. It's either trivial or non-trivial. So one can take a Z2 trivial band structure, but with strong SOC, take that kind of superconductor, and then put the magnetic ion on it, deposit on it. And one should see vortices. One should see a billion vortices, perhaps. And then if it's Z2 non-trivial, it's on the other side, then the vortices are actually non-abelian. Yeah, you're absolutely correct.
Thank you.
Any other questions?
Can I ask a question?
Yes.
Okay. So you're saying, but isn't niobium that? But there's another additional thing you need, right? You need the Fermi energy to be low. Is that true, Zikang?
Absolutely. Yeah, that's on the condition of nucleating. Absolutely. You're absolutely right. I need the Fermi energy to be, well, you need this, you don't really, you need the gaps to be comparable to the Fermi energy, right? You need superconductors close to the quantum limit.
Okay, so that's why niobium diselenide won't do.
Right. So in fact, a lot of superconductors, when they measure the vortices, they see a peak at 0, but that actually has no zero energy state. It's just a continuous state going through 0.
Sure. But what I'm saying is, for your particular scenario of a magnetic impurity on some conventional superconductor, so you need the condition that you need strong spin orbit coupling, and you need the Fermi energy to be comparable to the superconductor gap. Those are two important conditions.
Right, and that's why those two conditions are satisfied by FTS and lithium-111.
Okay.
In fact, if you put in the numbers for lithium-111, you would get it's in the quantum limit. Yeah.
There's another hand raised by Tamagana.
Hi. So I have, I don't know if this is something you may have covered, but so when I'm thinking of the system, there's the Z2 invariant topological band structure, and then there's superconductivity. And then I guess if you add the iron add atoms, and you consider the iron add atoms, if you consider them to be represented by a Zeeman field, then in the vicinity of these add atoms, there's a region where the field is magnetic field dominated, and surrounding it is a region where the gap is superconductivity dominated. I guess that by itself is enough, in at least in Fu and Kane's prescription, to give you zero energy bound states. So what I didn't get is, what is the evidence for the vortex? Because all of these experimental signatures, the magnetic field, they would pick up if there was a magnetic add atom, and the add atom was up in some ions and down in some ions. But what is the signature of the vorticity or the quantum anomalous vortex as opposed to?
Okay, very good question. Yeah. So as I was emphasizing in this, I think here. Right. So here, there is a magnetic atom somewhere here, and there's a line cut going through it, right? And what you see is there are a sequence of quantized states near this magnetic atom. And this sequence of states are integer quantized. So minus L2, minus 1, 0, plus 1, plus 2. And they're quantized in a way that is exactly like what you see in magnetic vortices. So this is just totally from experiment, right? For example, you are not going to see, if you just have a Zeeman coupling, right, in a conventional superconductor, what you see is you'll see a Yeshiba state, right? Not at zero energy, but you see a spin split state. Well, this is what you see.
I see. So if you had...
This is what you see exactly at type 2 add atom. You see these two peaks, they are the primary Yeshiba state that disperses away linearly with magnetic field. Whereas these states right here, this is field up to 8 Tesla. You don't see the zero energy mode move, right? There will be slight motion of other states, right? But the zero energy peak would not move.
I see.
Yeah,
so the evidence for there being an anomalous vortex is that doubling from half to a full delta square over EF.
Right, that's additional evidence. Yeah, in addition to the zero one, it's the doubling. And I would like to, that's why I wanted to finish with this page, that you can directly observe vortices. See, Yihua's group, and I think they're in the process of putting STM tip on top of the squid coil, but without STM tip, he will say nothing about the core states. But what he said is that in zero field cooling for FTS, you are going to pick up these spontaneously nucleated vortex and anti-vortex pairs. And this total flux, if you integrate this, actually is quantized. And the most amazing thing are these guys, if you can see my cursor, they carry one flux quantum, the red one, and the blue one, -1 flux quantum. And these are really genuine zero field, zero external field quantized vortices. But of course, they have to come in pairs because there are no field. Therefore, the field line has to go from one to the other, from the vortex to the anti-vortex. So these are evidence beyond. From a theoretical point of view, what is really, if you ask me, what is the fundamental reason that there are vortices coming in these class of materials? It's because of the magnetoelectric coupling, if you wish, the magnetoelectric effect, which is the essence of also quantum anomalous Hall effect, is that you can have magnetic field, you can have magnetic moment induce current circulation. That's the fundamental origin.
And we also have a short question from Igor.
Yes, so just to confirm that I've understood things correctly. So your explanation for type 1 and type 2 atoms is that they reside on two different types of superconducting state with TSS and without TSS.
Exactly, two kinds of surfaces at least. I think the bulk is.
It's not necessarily two kinds of surfaces, because as I say, according to this archived paper that I've just attracted your attention to, is that what we find is the state is inhomogeneous in the vicinity of the transition between the trivial superconductivity and non-trivial superconductivity. And so the inhomogeneous, it's like in cuprates, the electronic state is inhomogeneous, and you have islands of trivial and islands of non-trivial superconductivity on the same surface.
Okay, yeah, that's exactly correct. Yeah,
thanks.
It could be even the surface states are always there, but the surface state themselves are actually inhomogeneous. right? Some of the Dirac point is actually deeper.
The Dirac gap, actually, they have a Dirac gap which varies with tellurium content.
Exactly. That's what I'm saying, using to explain two different behavior.
We have experimentally quantified all that in that paper. That
I see.
The size of Dirac gap is a function of tellurium and iron content in the vicinity of the transition.
Excellent. Yeah, that should explain all these phenomena of observing both kinds of vortices.
Okay, thank you.
Yeah.
Thanks for an excellent talk. Thank you.
Yeah, thank you.
NVIDIA?
Yeah, very, very quickly. So Ziqiang, your statement about strong spin-orbit coupling was a statement about the superconductor, not about the impurity, right?
Not about the impurity. Although impurity induce a local, so it's called the Elliott-Yaffe effect, local spin-orbit coupling, but that is not essential.
Yeah, okay.
Yeah.
Okay,
yeah.
thank you.
Thank you all. Any other questions? I guess if not, I guess we thank Zhijiang and all the speakers very much for this wonderful session. And we will continue in about 8.5 hours with our night session.